Yeah, so you can convert this to hours and use the kilometers per hour, or you can convert this into meters per second. It's a simple thing if you really think about it. If you don't know. I know, I saw that in then you did, yeah, you did the second part.
And then to this one, for this one, I want to just fit 4 squared.
Yes, we did this first one.
Yeah.
It's not even really this.
Yeah,
I don't know.
I wasn't sure about that one. I figured out that one we went through after class. And then I guess for this one, I just messed it up.
That these are all in delta V, so that means F minus V. Okay? And this has a direction, you have to take a preferred direction. It goes in and comes up, you know what I mean?
Yeah.
So if so this is a negative, this is a negative, total one is going to be negative. It's not just a 3, you have to add this. So it's going to be 47 for point blah blah.
Okay.
That's the problem. You understand that?
I think so.
It's very important to understand. Going in with what 25, right? Out to the 22 or whatever. Now acceleration is defined as delta V. You got that part, right? Delta V, delta V. And this is you have to take a preferred direction. Let's say going in.
So that's why it will be negative 22.
And this will be F minus I divided by VF is coming out, so that's going to be a minus. The I is going in, but still it's a negative. Okay? Yeah. This was 6. 8 over 6 plus 2 over 3 plus 10. So that plus 13. Yeah. Now, what you have is not a test. So you're calculating this. Okay. That's the complementary angles. Understand? Those are tricky things. You have to think. Yes.
Is there a direction for this angle, or does it just not exist?
No, you can. There is another way to do that. That will be what? So this is 34. Then you divide, add the 90, and then give it from the x.
Right. Thank you.
So when you're describing the forces for M mass of Earth and M, you put directions on those, right?
Yep. But the equation tells you only the magnitude. You have to go to the problem and look at, okay, always the forces are towards each other. Because one force will be totally opposite direction as the other. They are always pointing towards each other. All that equation tells you is what's the magnitude of each of those forces. Then you look at the picture and say, okay, this is to my left,
Okay.
right.
And what I was asking, I know I brought up friction and stuff like that. When you were saying what forces were acting on it, that's the first thing that came to mind because I thought we kind of touched on it, or maybe we didn't. I can't remember.
No, I told you that we are assuming that there's no friction.
Oh, okay.
That's an assumption. That's not realistic, though.
Okay.
It's an idealistic situation.
Yeah, because.
But we'll soon get into friction.
Okay, so for right now, we're just taking whatever you give us. We're not going to add anything.
If the question does not mention anything about friction, do not worry about it.
Okay.
Either they have to tell you about a frictional coefficient or the frictional force. This much, then only you got it.
Okay. And then you said you just unlocked the worksheet 4.
Yep,
Okay.
4, 5, 6 are open. But you know what the questions are. I haven't opened that in Webb's and I'll open that.
Oh.
This is in Canvas.
Oh, okay. And when is that due again? You said the day before the quiz or something like that? I mean, day before the test?
Yeah, actually, projectile motion we finished last time, so I'll have that due Monday. And then today we can finish probably. Today I might not be, but whenever we finish a week from then, we'll have the courses.
Okay. Is there something that's due on Thursday?
Homework is due Thursday? Oh, yeah, I said that in the lab, right?
For what?
You said the homework was due Thursday.
Yes, that's the projectile.
Or last Thursday you said the homework was due Thursday. That's just it.
I haven't even opened that in the web assignment. I better do that. God, I won't get to sleep tonight. I have to write this recommendation letter, then sleep is a luxury.
I won't ask till the end of the
Huh?
I won't ask till the end of the
Alright, let's get back to this. So, you can say that your weight is equal to this quantity here, G me over R squared times your mass. Or else you can say that gravitational acceleration on any planet is equal to the G mass of the planet divided by the radius squared. That is true for any planet. Alright, so that is gravitational force. And keep in mind, this is only true for if the object is on the surface of the Earth. If it is further away, what changes now?
The acceleration?
Your distance between this and this is not going to be r sub t, it's going to be that. Some questions will give you that this is a radius of the Earth above this Earth. That means this is going to be r sub e from the surface. So what's the total distance between centers now? 2 r sub t. Okay? So be careful about those numbers. We'll work out a few problems later on. A separate section for that. Alright, next topic is Newton's third law. All what this one says is there's an equal and opposite force acting on. When the book was sitting on the table, it was acting downwards, equal and opposite force acting on. Okay. We proved that equal and opposite force was acting. Okay. Weight was acting downwards, Fn was equal and opposite, Fn came out to be the same as the weight. Okay. That's the meaning of Newton's third law. Application of Newton's laws, we already talked a little bit about it. We'll do a few more. This is like a recipe. The book gives you, read the problem carefully at least once. Yeah, if you don't read it, you can do the problem, that's pretty obvious. And draw a picture of the system. And then label each force, that means Fn's and Mg's and so forth. And draw a free body diagram. That's the most important thing. If your free body diagram is messed up, your whole calculations are going to be. Apply Newton's law in the compounds x and y direction. If you remember in the force table, you had a first activity you did was you had a pulley and then equal forces on either side, remember? So what was the net force acting on the ring at that time? Zero, because one force was to your right, so to speak, the other force was opposite in the other direction, right? So net force acting on the ring was zero, that's why it was centered around the peak. That was the constant. So if the net force is equal to zero, that means your left hand side is equal to zero. What should be your acceleration? Zero. Because zero is equal to mass times acceleration. Mass is not zero, it has some finite mass. So acceleration is zero. So when there is no net force acting on an object, acceleration is zero. That's what this objects in equilibrium means. Net force is equal to zero. That means if you look at the x direction, net force is zero. If you look at the y direction, net force is equal to zero. There are two possibilities for this one. When the net force is equal to zero, we know acceleration is zero, right? That's what we just said. Acceleration is zero. When can the acceleration be equal to zero? No, that is true. An object is just sitting, not moving. What is the acceleration of the object? Zero. It's not moving, right?
Right.
Then there's another time when the acceleration is going to be zero, but the object is moving. Constant velocity. It's going at constant velocity along a line. What's the acceleration of that object? Zero, because final velocity and the initial velocity are the same, right? Nothing changes. So delta V is going to be zero. So there are two ways your object can be in equilibrium. That is, equilibrium means your acceleration is zero. Okay? The very common one is object is stationary, sitting, not moving. The other one is it's moving with constant velocity. Still the acceleration is zero. Those are the two possibilities. Before I go anywhere, let me explain this in a little more detail. Some students have trouble with this concept. When you have a pulley and string attached to that and weight put on one side, this is subject. You have two masses. This is a pulley. We assume all the good things, no friction. Pulley is massless, and the strings are, don't stretch. We assume all that, and then you have two different masses put on them. They are different, not equal. Okay. Now, let's say for sake of argument, M2 is larger than M1. Now I hold them, let it go. I take my hands off. Okay, what will happen? M2 is heavier than M1, so M2 is going to go down, pulling M1. Understand that? Till it goes and hits this one is the ground or whatever. So we are not interested in that part of the motion, we are just interested in the motion till it goes and either it hits the pulley or this one drops out. Okay. Now, in a situation like this, you see that one string goes over the pulley and is attached to the other. Okay. Moment I let it go, this one is going to go up, this one is going to go down. What is the acceleration of M2 and M1? Very important thing is not the acceleration of gravity. A lot of students get confused. They write the acceleration of this is G, is going down with 9.81, this is going up with 9.1. Why isn't it 9.81? It's not free fall, right? It's not just falling by itself. This guy has to pull this guy up, right? You see that? It's not free fall. That's the whole reason. When would the acceleration be 9.81? When it is free fall. That is, it's all by itself. There's nothing else. The whole thing is coming down by itself. Then it is 9.8.
Net force?
Huh?
Is it the net force?
Net force is just the weight. But here the net force is not weight only. There is some other forces. That's what we are doing. And keep in mind that when you have these masses acting on that, attached to a string, this tension. Tension is pulling this thing. Okay. And then at this end of the pulley, the same tension is acting down. That means pulley is getting pulled by this tension. The way to look at it is now, if you were to look at this pulley part, I have the pulley surface here, I have the mass. Okay. Now the string part is from here. Okay. Always the tension is towards the inside, towards the middle of the string. Okay. That means tension is in this direction here. In this end, tension is towards the middle. That's how you mark it. Don't get confused with this one. That's why I'm doing this thing in a little more detail. This is the string part. One end is here, the other end is on the pulley. Tensions will be pointing towards the middle. Now we come here. This is one end of the string, that is the other end of the string, right? So the tension should be here and same tension here. That happens only when we assume there's no friction on this pulley and the pulley is massless. Okay. When the pulley doesn't have any mass and there's no friction, tension everywhere is the same magnitude. Okay, depending on where it is, either it is pointing this way or this way. Make sense? How do you handle that? You look at the two ends of the string, and always the tensions are towards that part of the string. Yes. Say again. Alright, so you look at this part of the string. One end is on the pulley, other end is on the mass. Right? The mass that is hanging. That's what I drew here. Two ends here. Now the tensions are always to the middle of the string is here, right? You see that? The tension should be pointing towards that middle, this tension should be pointing towards. Look at this guy here. This is one end, this is the other end. Tension should be pointing towards this at this end. At this end, the tension should be pointing this direction. Okay. And if it is frictionless, and if you assume this pulley doesn't have any mass, tension is all the same no matter where. The value of the tension. Okay. But the directions depend on where the two ends are. So on the pulley is getting pulled by 2T downwards. This mass is getting pulled up by T. This mass is getting pulled up by T. Actually, that's the tension that makes it go up. If you didn't have the string, this one will not go up, right? Because of the string tension, this gets pulled up. Okay. Now, we want to find out that now the question would be, for a situation like this, what is the acceleration? What's the question? These are typical questions. I'm gonna put some values for this M1 and M2. Let's say this is 10 kg and this is 5. Now, and keep in mind that when this guy comes down 5 centimeters, what will happen to this guy? It has to go up by 5 centimeters, right? Why? They are attached, like, you know what I mean, together by the rope, right? So this, whatever this guy comes down, this has to go up. It's like a solid body, rigid body, right? One part goes some amount, the other part, every part has to go up, go that amount, right? Let's say that the speed of this one is 10 meters per second. What should be the speed of this guy? 10 meters per second. Acceleration of this is some 2 meters per second square. What should be the acceleration of this? 2 meters per second. It acts like a one solid body. If the body is going this way with some velocity, all the parts of that body is going with the same velocity. Okay? Same thing with the acceleration. That's the concept. Now, you see that we have the masses, we are trying to find forces acting on that and accelerations acting on that. What concept comes into play? Newton's second law of mass. That's how you break down the problem, okay? I'm given masses, I'm being asked to find a tension, that means force, okay? I'm being asked to find an acceleration. So how does the mass, force, and accelerations, get related? Through Newton's second. Okay? So the moment you see a problem like that, the flag should go up. Oh, this is the Newton's second law. lot of students have trouble with that. So if that practice tells you, practice is the one that can help you to figure out. You read the question and say, okay, what is this? And is it a kinematic equation thing, or is it resolving forces? Is it a Newton law thing? That takes practice to bring that. Lot of students, once you figure it out, you write the equation and then it just natural. Alright, so we figured it out. This is going to be a Newton's second law problem. Why is that? I'm given the masses, I'm being asked to find the acceleration and the force. The force, acceleration, and masses are related by Newton's second. What's the very first thing we have to do? Say that again? Yeah, that is true. But before that, before we start any of that, we have to do something else for Newton's second law. Free body diagram. Okay, that's the very first thing you ought to do before you do anything. Then the Newton's second law is involved. Okay, I have two bodies here, right? 10 kg and the 5 kg. That means what? I have to draw the free body diagram for each object. Okay, I'm going to draw the 10 kg. Let me blow it up a little so that we will see more details here. This is what I have. Okay. Now, what is the very first force I'm going to draw on this? Gravity. What's the direction of the gravity? Down. How much is it? mg. So what is that? 10g, not just 10. mg. Okay. M is 10, g is 9.8. Okay. What else? Am I done? Why not, Sydney? Yeah, what do you call that guy? No. There is no normal force here. Why not? It's not sitting on anything. It is just going up and down. Normal force comes when something is sitting on something. Okay? No normal force. But there's another force here. Tension. The string is pulling me down. Okay? So there is another force here. What is the value of that? T, which we do not know, and that is upwards. Why? Because if you look at this string here, this is one end of the string, right? The force at that end is always towards the middle of the string, which is upwards. Okay. So I drew the free body diagram for this one. There's something else I need to mark here, though. This is going downwards with an acceleration a, which I do not know. I'm trying to calculate. Now I have all the information I associate with that one. That's how I draw it. Now, who can draw the free body diagram for the point? Yeah, it is heavier, so it's going down. Acceleration is obviously in that direction, right? So it's going to speed up as time goes on, right? Keep on going down, but not 9.8. 5 kg. How do I draw this free body diagram? Can you come and draw the free body diagram for me?
First I'm gonna know.
What is the very first force you draw when you have a mass? That's the very first thing you ought to do. How much is that? 5g, okay. What are the forces there?
And we're going up.
Yes. What is it? What is pulling it up?
You have your attention and you have the two forces.
What are the two forces?
The tension and you have the other mass.
That mass is the one that is manifest as tension on this side. Because there is something hanging on the string, that is creating the tension. All what it has is the tension and the weight of it. Yep, that's it. That's the free body diagram. Make sure you don't get confused because this mass has nothing to do with this other than it creates this tension for it to get pulled up. Okay, that's all. Because this is going up, isn't it? Lighter guy is going up, heavier guy is coming down. So whatever this one comes down should be the opposite sign but the same magnitude. That's all. Make sense? Maya, are you okay? No, that was a mistake. Tension is upwards, you know what I mean? So same tension because I said it's a frictionless, massless. The tension values are the same no matter where you are on the rope. But you have to be careful what direction. This is one end of the string here, tension is up. This is another end of this other string here, tension is up. If you were to worry about the pulley, the tension of the pulley on this side will be downwards, tension of the pulley on this side will be downwards. But we don't care about the pulley. Yeah. Now I have the two free body diagrams. Yep.
Going back to this was before the break, so we said when we were denoting a direction,
yep.
So like we would have the summation of forces and we said going up equals whatever it is. So why wasn't it that like we're choosing a direction and that direction represents the summation of all the forces? We were only looking at it in terms of vertical or horizontal.
Here the forces are only vertical, right? There's no horizontal force.
But I mean, like the way we did F net equals MA.
Yeah.
Like, let's say we just have a box here. Why is it that we're looking at the horizontal and vertical individually instead of just looking at this like, summation of the forces and then choosing a direction?
You mean to get the resultant force of the normal force and the other applied force, right. And you can do that.
Okay.
Yeah, you can do that.
So. Really quick for your erasing thing.
Yeah.
So the FG is just our weight.
This is the weight of this mass. That's the weight of that. Yep.
So if it was asking about the tension like on the pulley, it's specifically saying the problem.
It will be 2T.
2T.
Yeah, because this pulley is hung by some kind of a frame, right? What is the two forces acting downward? That is T. T here, so it should be equal to what? Pulley is not going up or down, right? It's stationary, it's in equilibrium, right? That means what? Whatever the force is upward should be equal to whatever the force is downwards, right? Okay. There are 2T and then this force on the bracket would be 2T. Make sense?
I think so.
Thanks.
Like I understand that it's like it has to be like the same amount of force in the opposite direction.
Yep. That's only when it's going to be in equilibrium, right? There are 2 T's acting on either side, so the total downward force will be 2T. So that should be cancelled out by the total upward force of 2. That's how the pulley is not going up or down or anything like that. For some object to be stationary, that means all the net forces acting on it should be 0. Mm-hmm. That means if there is a force on the right, equal an opposite force on the left. If there's a force downwards, equal an opposite force upwards. Okay. You have to have all that. Alright. So I got this thing, now I'm gonna, now I marked, I did the free body diagram. Why did I do the free body diagram?
So you set up the equation.
To apply what? What kind of problem are we working on here? Newton's second law problem, right? So I drew the free body diagram, then what is the next step?
Draw the vector equation.
I write the second equation, Newton's second law, I write that equation. What is my equation? Before I do that, I'm going to write the equation for this guy. What direction should I use? Downwards, because it's going downwards, right? Downwards, what is the equation?
Summation.
Summation of forces should be equal to mass times acceleration. Alright, now I'm worrying about summation of forces. There's 2 forces acting on this, right? One is the weight, the other one is the tension, right? Mm-hmm. Alright, let's start with the weight. This is downwards. My preferred direction is downwards. How would that tension come here? Positive. My tension is upwards. My preferred direction is downwards. How would the T come in here? Negative. Should be equal to, what is my mass here? 10. What's my acceleration? A, I do not know. Unknown, I don't care about the direction. My math will tell me what the direction. Okay? I know it is going downward, so my acceleration for this has to be downward. There's no other option for this. So this is my one equation. How many unknowns are there? Two unknowns. Can I solve for any of them? No. Then how would I do it? I write the same equation for the other one. Two equations, two unknowns. That means simultaneous equations I can solve. Understand? Alright. For this one, what is the direction that I should use the Newton's second law? Upwards. You see that even before you write a vector equation, decide on direction. Otherwise, you are asking for problem. Alright. Here I'm going to first talk about t. My t is upwards, my preferred direction is upwards. How would the t come in here? Positive. 5t is downwards, my preferred direction is upwards. How would that come in here? Negative 5t. My mass is 5, my acceleration is 2. Now let me write these two equations. This is some simultaneous equations. I'm sure you have solved them before. There are two ways to solve them, right? Actually, there are more than two ways. Most common ways, two ways are substitution or else what? What else?
Elimination.
Elimination or substitution. I'm going to write the two equations, one underneath. Ng minus t is equal to A, and the other equation is t minus 5t is equal to 5.
Do we have to make them go in the same direction first?
What do you mean?
Because this is like this one's going down and this
Just a
one.
minute. I took care of the direction because everything is downward, so according that's why the negative t came here. They don't have to be the same direction for you to solve that. But only thing is when you take a preferred direction, you have to be careful about whether this is positive, that kind of stuff. The moment you do that, you get it. Now, what is the smartest way to solve these two equations?
Just add them together.
Add them together, elimination method. Why is that? You have a negative t and a positive t. When you add these two, the t is cancelled. Okay? Or else we can say t is equal to 5a plus 5t, go and substitute. It's the same thing. But I think adding the two is smart. Okay, so the g's will cancel out. I get 10g minus 5g. Should be equal to 15a. So this is 5g. It's equal to 15a. A is equal to 5g over, which is g over. How much is that? 3.27 meters per second. Do not worry about the direction here because I already marked the directions here. Because for this one it will be one direction, it will be the opposite for the other one. Okay? All what you need to do here is to get the magnitude. I have already marked it. Depending on the which one is heavier, that will be going down, lighter one will be. Makes sense? Now I have the A. Now the other question is what is my T? What do I do? Go to any of the equations here and substitute. Easier thing would be this because the numbers are smaller here. I'm trying to find t minus 5g is equal to 5a. I'm going to substitute. I'm going to take this guy to the other side. It's going to be a positive number now. 5 times a is 3.27. And somebody tell me what the addition of this is. Should be 45. This is about 15 something, so close to about 60 something. How much? 16.35. Yeah, add the 2 and 2. 65.4. What are the units of this? Tension is what? A force. So this should be newtons. I found the tension, and even in tension, don't worry about the direction because I have already marked the directions. Are you all right with this? I have given something like that in a test.
So as long as like during an test, as long as we mark which directions they are, then we don't have to worry about saying anything once we remember them.
Yep. So you have already marked that direction, then you're just telling me what the magnitude and the sequence that's all. It depends on what mass you're talking about, whether the direction is going to be up or down. So based on the mass, your direction is opposite. All right. So now we have a little bit understanding how the tensions work. Okay? Now let's go into going back to your question. You said why did we? I had a 10 Newton here, right? And then I had a 5 kg mass. There was a weight acting downward. There was no. Now you ask me why don't I use the net force and then get the direction and then do that, right? What is the net force acting on this? If you consider all the directions. There's no, these two don't contribute at all. The net force was the same as the the next direction.
Let's say you had been pulling
Yeah, with a different direction. Then of course it will be going at an angle like that. Then you can do it. All right. This has a resistive force, like a friction or drag force or something. So always remember that friction always opposes what? The motion. If the object is going to your right, what will the direction of the friction? Your left. It's always opposing the motion of the object. Okay. So if the object is falling down, the wind resistance will be upwards. So, memorize the steps, draw a diagram, then draw the free body diagram, select the direction, write the Newton's second law, and then figure out what quantities are positive, what quantities are negative, and then solve for the answer. That's the recipe. You need to memorize the recipe. Now let's look at part A. Before that, let's read the question. 1000 kg car, what is that? What symbol can you assign to that? Mass, M, okay? So it's traveling at 60 kilometers per hour when in neutral, the speed drops to 40 kilometers per hour after 5 seconds. So what is that 60 kilometers per hour? What symbol can you give it to? Initial velocity, that's what you started with. Then 40 kilometers per hour, what is that? Final velocity. What is that? 5 seconds means? Time. That's how you handle the problem. Now you know the mass, you know initial velocity, you know final velocity, you know time. What's the first part is asking? Average drag force on the road. It's asking for a force, right? How would all this data relate to that force? Yep.
Use the line contribution that you had said with momentum. I'm not sure it was right. So what I did was mass times the velocity final minus velocity initial over the previous time. So I did 1000 times 60 minus 40 to 5.
Yeah, that's right. But before you go there, average drag force, it's asking for a force. How would a force relate to all that data that is given through what concept? That's my question. You went through a lot of details. I was just asking for the concept. What? Huh? Yeah, the Newton's second law, right? Newton's second law is involved. Why? They're asking for a force. They have given some speeds. They have given a mass. You see that? What is that speed good for them? To find the acceleration. Okay? So that's how your thought process should go, how to analyze this problem. They're asking for a force, that means it should ring a bell. Okay, this is something to do with Newton's second law. Okay? And do I know my mass? Yes, I know my mass. Then they have given some other information. What should that information good for? To find the acceleration. The moment I find the acceleration, I can use Newton's second law, sigma f is equal to mass times acceleration, and try to find the drag force. Moment you are in neutral, what is happening now? Engine is not providing any force to the car, right? So what are you now? What force is acting on the car when you are in neutral? Only the drag force. Engine force is not applied to the wheels anymore, right? You are in neutral. Or else you can cut the engine off. And then what's happening? Now the drag force is acting on the car. Only force acting on the car in the horizontal direction will be drag force. Okay? And that force, that's what we are trying to know. And what would that drag force do to the car? It's going to slow it down, isn't it? Why? It's acting in the opposite direction of the motion of the car. So eventually it will slow down, and ultimately what will happen to the car?
Come to a rest.
Come to a rest.
But then wouldn't that be a deceleration or basically an acceleration?
It's a deceleration. It's a negative acceleration. So your acceleration going forward should be a negative. If you didn't get that, then something went wrong.
Right.
That's what the sanity check I was talking to you about.
Okay. So we should have just one acceleration though, because you're going to the right, and you're still doing with drag force, right?
Yeah.
And then when you hit neutral, that's when the drag force takes over. So it's still.
Yeah. Before you get into neutral, the engine is applying a force to overcome the drag force. That's why it could go, with some speed. It could even accelerate depending on the engine's, what it is. Or it could be just cruising. It could be cruising when can the car cruise? You know what I mean? There is drag force always applied. For it to cruise, that means that going at constant speed. What should happen? Grant? Zero acceleration. That means what? There is a drag force applied on the car. So that means.
Oh, so it's decelerating.
No. It's cruising. Cruising means there's no acceleration. It's not decelerating. It's not accelerating. Acceleration is zero, as it said. Then the car engine should provide what? Force equal and opposite to the drag force. What's the net force acting on the car then? Zero. What's the acceleration on the car? Zero. So whatever the speed it has, it will keep on going with that. That means the car engine should provide the force equal to the drag force. But when you are neutral, car engine doesn't provide any force. All it is under the mercy of drag force only. The only force that is acting on the car is the drag. Alright, who can work this out for me? Let's see. Fine? Alright. Bring your calculator. You are missing a force. Where is the car? Is it flying through the air, or is it on dirt, or is it on a road? If it is flying through the air, then there won't be any normal force, right? If it is touching something, then it has to have a normal. Pay attention. P sub 0, what is it? Read the question again. Don't make mistakes like that. 60 what? Kilometers per hour. You know what I mean? Go to the question and then, you know what I mean, look at each and every term. You know, don't make a mistake like that. It's a shame because you wrote down the given information. Usually the time is indicated by a load. After this case for then positive, negative, did you go through the mental process? Okay. Look at what are the units of velocity? Yeah, you have two choices. You can either convert that into, yeah, but only thing is then you'll get your acceleration in kilometers per hour square. That's not going to help you with the second law of Newton's second law. So you're better off converting all that to meters per second. You're not done. Okay. With more practice, maybe you can write 1 hour is equal to 3,600 seconds. You know, that's up to you, but this is perfectly okay. What's the significance of negative sign here? Acceleration is to your left. Okay. All right. Now we found the acceleration. What is this good for? Okay. How do you do that? Put the half arrows on top of it. Should be half arrow on top of it. Those are the vector quantities. What direction are you using this? Okay. You got it, right? Okay. It's up to you. You don't need a calculator. You move the decimal 3 times to the right. What are the units? See? Here. Does it make sense?
There was you told her that she didn't need a negative sign.
You could write the same thing if you were to write it on to the right. Now it'll come up with the negative.
That's right. She did go to the
Yeah,
right.
she
Okay.
applied it to the left to prevent that negative. It's up to you.
Okay.
That's part A. All right. Now, how do you do part B? How far the car travels in 5 seconds? Okay. Huh? Yeah. What direction? Remember, before even we write any of this, we write a direction. Get into that habit, otherwise you can easily get into trouble. So you got it memorized now, huh? Okay. Accelerations.
Oh, do you want me to base off this?
1.1. You need that's. But you got something different?
I think I.
It sounds right.
I
1.2.
So I did significant. I did the significant
Oh,
figures.
okay. It's just take. Let's not worry about significant. Take it as negative 1.1. Everybody understand what she did? Now you see that how far the car travels in 5 seconds. That has nothing to do with Newton's second law, right? Distances and all that. How is that come to play? That is to the kinematic equation, right? So that's You need to be able to discern those things, when to use, what. They ask him for how far the car would travel, so that means, kinematic equation number 2. You stick to the right because it's still going to your right, although it's slowing down, still going to your right. Okay? And so it comes out to be 69.5. Yep, Sydney?
If her preferred direction is for the left, why is our answer positive? When I thought the left is negative.
No. The acceleration is negative to
That's
the right.
how far. Yeah, that's
So going
how
to
far.
your left is positive. That's why there's no negative sign.
Distance.
You said acceleration is negative, that means point.
Negative going to your right. You know what I mean? See this thing? She's using it to the right. It came out to be negative. Here she's using it to the left. That is going to be positive. Whatever to the now, if your preferred direction is to your right, if this is negative, when you use it to the left, this will become a positive.
Why is the car is in neutral, why is the car going to?
Oh no, she didn't want the negative sign. That's why. It's up to her. You know what I mean? Car is still going to your right. You have a point there, but she didn't want the negative going to your right to be negative. You know what I mean? You end up with a negative number here, right? If you were to take the preferred direction to be right, she'll have a negative. She didn't like the negative number, so she took it to be going to the right, going to your left hand. Some people don't like negative numbers, some people like just to use it in the direction of the motion. It's a choice you make. Are you okay with that, Sydney? You still look puzzled. If anything, going to your right is negative, that means it is really going to your left. That's the meaning of this. Took your preferred direction to be right, you came up with a negative number. So that means what? The true acceleration is to your left. That's why she took it to be in this direction, because acceleration will be positive. If she were to take it to be preferred direction to be right, this whole thing will be negative because this one will come in as a negative number. Your force is going to be negative. What's the meaning of that? You took your preferred direction to be right and your force comes out to be negative. That means what? Your true direction of the force is to your left. That's the meaning. All right, let's do number 2. How would you handle this problem? you're given a mass, right?
Mhm.
And then you're being asked to find a force. What concept is involved here? Newton's second law, okay? And now you know the mass, and so to find the force, what else do you need? Acceleration. So rest of the information that's given to you is to enable you to find the acceleration. Okay? All right. Now you're given an impact time was 0.2. That means your foot is in contact with the ball for 0.02 seconds. Okay. During that time, what happens to the ball? What? So
It goes from 0 to some sort of final
exactly. The
acceleration.
initial velocity of the ball is how much?
0.
0. It was at rest. Okay. Then the foot came into contact. Then the foot is driving the ball, right?
Mhm.
Then when it leaves the foot, it had about 15 meters per second. So your visa initial velocity is how much? 0, because it was at rest. What is that? What is that 15 meters per second? Final velocity. Okay, this is when the foot was in contact with the ball. Initial velocity was 0, final velocity was 15. Okay, what else is given to you? The time for that motion. Okay, this is all about when the foot is in contact with the ball. Okay, foot is in contact with the ball and then ball takes off, with 15 meters per second. We are only analyzing that part of the motion. So the time is given to be 0.02, initial velocity is 0, final velocity is 15. What is that good for? Acceleration. Moment you know the acceleration, you can calculate the force acceleration.
Do you need to convert 500 to kilograms? Or?
Of course.
Okay.
Why?
That's a standard.
That's SI. Otherwise, you cannot write the force to be newtons. That's the whole thing.
Right.
I want all my dimensions to be in SI. That way, the moment I get a force, that is newton. The moment I get an acceleration, meters per second square.
Right.
That's how I do it.
That's essentially like the same problem. It's like the first part of the problem just did.
Exactly. This is similar to the exam question I gave you, right? The ball comes and hits, you are given the time that's in contact and it bounces back. You found the, acceleration from that if you want. Who can work this out for me? Should be several hands going on. Jasmine, you haven't come to the board for some time. Stand. Bless you. Use that now. So she's using the definition of acceleration, which is what? Vf minus vi divided by delta. Okay? An important thing is the directions here. Vf is going to your right, let's say, vi is 0. So now your acceleration comes out in the same direction as of the 15 meters per second. missing a hat around the bed.
So,
There is an issue. What is the issue? To recognize adjustment. What is it? 500 is given in what? Grams. What should you convert that to? Kilograms, right? How do you convert kilo? Don't need us too much. How do you convert grams to kilograms? Divide by what? 1,000. Just write.
Just write it.
Exactly. That's what. If you wanted, you could have just written 500 grams and convert that into kilograms. You know what I mean? But here, this is a stopgap thing. Yep. Everybody get that answer? Anybody else got a different answer? All right, thank you.
just, I was wondering about you did draw
Free body diagram?
yeah,
Yeah,
It
you
would
should
be
have
pretty simple, right?
drawn that, yes.
it would just be like a box.
Box with a horizontal force, you know what I mean, that's all. Just one force. There will be a weight acting downwards normal, but we don't care about that because motion is not in that direction.
Right.
We are only interested in the horizontal motion. It's immaterial what the y direction.
And just out of curiosity, that down direction would just be
mg and the fn will be
okay, it wouldn't be like 0.500 G.
0.500. M is 0.5, so mg is. This is an interesting problem. To find something different in this one. very important draw physical friction and draw the free body diagram. You're not sure how to do the forces? 20 degrees below the horizontal on a 10 Newton box. Huh? It's like a lawnmower you're pushing down.
Okay, so it's like off that inward.
Itself.
Okay, so it says what 30 newtons 20 degrees below the horizontal. This is the horizontal, 20 degrees below the horizontal. You can pull it here or you can push it here. Same thing.
And then what's the 10 newtons? Is that going in the regular direction or down direction line? Is that the
That's the normal.
You mean normal force?
10 newtons is the normal force?
And
We don't have the normal force.
That's the
Yeah,
weight,
there will
the
be a
weight.
weight. Let me first finish this thing. So it is 20 degrees below the. Because if I were to extend this out, do you see that this angle is 20 degrees? You see that I'm pushing it down. That is 20 degrees below the horizontal. You see that? It's the same as this angle being 20 degrees as well. You see that I don't have to draw this part. Everybody understand what I'm drawing here? This is 20 degrees below the horizontal. It's the same as 20 degrees there. I'm pushing down on like a lawnmower handling. I'm pushing it down. It's the same thing. Okay? Either I push it down or I pull it here. It's the same thing. Pull it at this end is equal to pushing it down at the other. Make sense? All right. What else? There's a mass with this, so that's obviously a weight W, right? What does it say? 10 Newton box, right? What is that? Weight is given to me. This is 10 Newton straight away. What is this? That is mg, right?
Yeah.
Mg. So they're asking what is the mass of the box. That's pretty easy, right?
Yeah.
Mg is equal to 10. So
Right.
how do you find the m?
98.1.
Divide that by 10 divided by 9. This is something what I talked to you about with the pulley to get a 10 newtons. What you have to hang, something simple. So mg is the weight, that is equal to 10 newtons. So m is equal to 10 divided by g, which is what, 10 over 9.1.
1.02.
Whatever, yeah, 1.02 or something, right?
Yeah.
Okay. That's what are the units here? Mass. So it's. You see that I don't keep track of intermediate units. I know everything is in newtons. So boom, I write my units. All right, that's the first part. Now, normal force acting on the box. I did not complete my diagram here. That's normal force acting on this. Always the normal force is perpendicular to what? The two surfaces that are in our main track. That means this box is sitting on a horizontal surface here. So that has to be perpendicular to this common surface. Okay? And so that is Fn is going to be vertical. Yeah. Box is on a horizontal plane.
Oh wait, because you have to account for the 30 newtons.
Now, do you see that this force is at an angle?
Mhm.
You don't like any angle business, right? How do you handle that? We solve it horizontally and vertically. Okay. Now, this one will have a horizontal component in this direction, vertical component down, right? So I'm gonna, in place of that box, that force, I'm gonna write these two. What was the value of this force? It's 30 newtons. in place of that, I have one force acting downwards and then this force. Everybody understand what I did? I have this force at an angle. I got a horizontal compound, I got a vertical compound, but vertical compound is pointing downwards because this force is going. If this force was going up, if I'm pulling it from that point, what will happen now? Vertical compound will be this direction, horizontal compound will be this. You see that? Depending on whether you are pushing it down or pulling it, those compounds are going to be, directions are going to be different. Alright, so now what would this be? This will be 30 sine of 20, right? This will be 30 cosine of. Now this guy is gone. In place of that, I have the two compounds. You see that? That guy was at an angle. I don't like it. In place of that, I have the two compounds, horizontal and vertical. Okay. Now I need to find the normal force. This is on the floor. The box is not going up or down. You see that? It can only go horizontally when it is on the floor.
So you only need one component?
Say that again?
Will you only use one component in this situation?
Yeah, to find the normal force, what we have to concentrate on. Horizontal one doesn't help me, right, to find the normal force. So I need to find, concentrate on the vertical direction. What is the acceleration of this box in the vertical direction? Is the box moving up or down?
Zero.
It's on a horizontal surface. It can only go horizontally. It's not going up or down. Okay? So I'm going to use vertical up as my preferred direction. Sigma F is equal to M. Alright. I have this guy. Is that going to be positive or negative? Positive. F and preferred direction is upwards. This is upwards. 30 sine 20. Downwards, preferred direction is upwards. Negative. Mg is downwards, preferred direction is upwards. So that's then. What's my acceleration? Zero. What happens to the whole right hand side? Zero. Okay, now my goal is to find this guy. That means I'm going to take everything to the other side. So if n is equal to 10 plus 30 sine of. The whole thing is 20.3. And what are the units? Makes sense? Now this is one situation where you cannot say if n is equal to initial. Why? There's a contribution by this angle force coming in. You have to resolve that and then you can apply whatever the forces upwards and equal to what. Make sense? So what's going to happen to the box? It's going to go to your right, right? Why? There is this compound of the force. You see that? That's the one that's going to slide it horizontally down. It's not going up or down, it's just going to slide to your right. Because of this. Make sense?
Can you explain that again?
Huh?
Can you explain that again?
This one has a vertical compound and a horizontal compound. So this box is not going to go up or down. It's only going to slide horizontally. This is the one that is going to make it go horizontal. If I want, I can find the acceleration of this box. How do I do that? Now, I'm going to write the Newton's second law in this direction. Okay. What is the net force acting in the horizontal direction? Only one force is there, right? That is to my right. My preferred direction is to my right. So that 30 cosine 20 comes in as positive, right? What's the mass of this box? I just found out 1.02 times acceleration A. So A will be equal to what? This 30 cosine 20 over 1.02. How much would that be? 27 points. Meters per second. So the acceleration is going to your right with 27.6 meters per second squared. Make sense? Alright. I'll see you tomorrow. What is due tomorrow? Quiz on the post table. Okay? Post table, remember? No, it's not due. There will be a quiz based on the test. Lab that.
Oh,
What lab number is that?
the results back.
Yeah, that's what's called post table.
Oh, okay.
Oh,
The finding the resultant and the equilibrium, you know what I mean? The ring thing, we centered the ring.
Is it like the same as the quiz?
Huh? Somewhat similar.
Okay.
No, you'll have to work out a problem.
Can we use our lab books too?
Yeah.
Just for lab.
Oh, wait, today? No, oh yeah. So today's quiz, all I got was Reddit. I'm not looking at it.
Yep.
Okay. Still can't remember what it is. 'Cause I had a question about. Okay, yeah. So.
I have blank.
Okay. So yeah. So when we were finding the. All right. So I listed my X, my T, my A, my V1. I call it V1 and then V2. Okay. So these were given when we have our X.
Oh, for the projectile motion you're talking about?
Yeah, we're
Okay,
focusing
it's
on
on
right now.
X.
Yeah, okay. So these were given, so I didn't have to do anything with that. Right? I didn't have to use cosine or sine for that, right? Because they're just the numbers, right? So did you have to use cosine sine when you start figuring out the velocity?
No, because this is horizontal.
Right.
It's going off of a cliff, so it comes horizontally and then jumps.
Right. So I didn't need to use any of that because it gave me the
This is straight away, this is X component, Y component.
Okay. Well, what about the velocity? Instead of use cosine and cosine, that would have been right. I wasn't thinking about it.
Oh, yeah, for that one.
Yeah.
I thought, this is, you're supposed to get an answer earlier, like a answer, like a number.
Yeah.
I thought the,
Oh, you could have said double that amount or what, that is fine as well.
oh, I didn't know that. I thought,
You could get a number for me, or you could say as twice as of that, or half of that.
but I thought that we were talking about the